All right. So this is called a Pythagorean identity. And the Pythagorean identity is highlighted there. It's sine squared plus cosine squared equals 1. Here's where that comes from. You might recognize it. It's called a Pythagorean identity because it corresponds to Pythagoras' theorem, which says a squared plus b squared equals c squared. Well, where are my a, b, and c in here? On the unit circle, the radius of the circle is the hypotenuse of the right triangle, and the radius of the circle on the unit circle is 1. So that's my C. Okay. On the unit circle, it just so happens that the x-coordinate is cosine of theta and the y-coordinate is sine of theta. Because, we have, by definition, cosine of theta is adjacent over hypotenuse, and so we end up with, if the adjacent is x over the hypotenuse 1, it just ends up being x. So x equals cosine of theta, and y equals sine of theta, and when you throw those in for a, b, and c, you get the Pythagorean identity for trig. That one you need to memorize. So cosine squared plus sine squared equals 1, you need to know. Now, you can create from this one identity 2 other identities that you might use. One of them would be to solve this for sine squared by subtracting cosine squared over. Another one would be to solve for cosine squared by subtracting sine squared over. And so they allow you to make substitutions in order to take an equation that might have a mixture of sines and cosines in it and change it to just one single trigonometric function. Okay? So this one Pythagorean identity then can be rewritten in 2 different ways. And then from this one identity, you can create 2 other identities that also can be rewritten in 2 different ways. So from this one identity, we can get 9 different identities. Okay, 9 different identities. What a deal, huh? So from 1, we get 9. You really only need to memorize 1, though. Okay, and then be able to do the algebra to create the other 2 here. Does that make sense in terms of how we solve for sine squared here? And then if you had sine squared in an equation, you could replace it with 1 minus cosine squared, and then maybe have the equation all in terms of cosine squared. It's like doing a substitution when you have x's and y's in the same equation. And we substitute to get it all in terms of just one variable, x, right? So here, if you divide each term by cosine squared of theta, you get yet another Pythagorean identity that involves other trig functions. So let's show what that looks like. Sine squared theta, if I divide that by cosine squared theta, and then I have to also divide each and every term by that same expression. And then I have 1 over cosine squared theta. And then it's like magic here. We're going to get another trig identity, Pythagorean identity, that involves other trig functions. So sine squared over cosine squared is actually tangent squared. So we have tangent squared theta. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared theta. And we could box that one. I'm not going to highlight it. I'm not going to memorize that one. I mean, we could, but we don't need to. We just memorize the first one, and that's highlighted there. And then remember that we can create one that involves tangent by dividing through by cosine squared. And then from that one, I could create 2 more, right? I could solve for either tangent squared, or I could solve for 1, I guess. Set 1 equal to secant squared minus tangent squared. The other Pythagorean identity I can create by dividing each term by sine squared. So let's go ahead and do that next. So if I take sine squared of theta and divide by sine squared of theta plus cosine squared of theta divided by sine squared of theta equals 1 divided by sine squared of theta. I get sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared of theta. And 1 over sine squared of theta is cosecant squared of theta. So with a little bit of algebra, I get Pythagorean identities that involve all 6 trigonometric functions. And they can be used to substitute in to get our equation in terms of one trigonometric function. So this is a perfect example of what they talk about in the Common Core language. They'll talk about seeing forms of quadratics or seeing forms of equations. In other words, the sine and a cosine and tangent represent variables. And so you're going to see quadratic equations that are in sine of theta. In other words, instead of x, there will be a sine of theta in there. So you might see 3 terms in there, okay, like a trinomial that you factored before, but it's all in sine of theta. And that's a pretty big deal as we move into calculus, is being able to see that, because it won't just be with trigonometric functions, but any function can take the place of x. Okay? And then you apply your techniques of factoring and your quadratic formula to solve it. Okay? We'll get to those in a little bit. So starting with the first one here, it says find all solutions. So we will do that. We're going to throw out our domain. Don't worry about the domain of these. Okay, so forget about that. We're going to find all solutions. That means we're going to have to write an expression that covers all the solutions that you could possibly have. Now, what we do to solve something like cosine of theta equals root 2 over 2 is we take what's called inverse cosine of each side. That's what it looks like. We take inverse cosine of each side of the equation, and inverse cosine of theta is just theta. And so we end up with theta equals inverse cosine of root 2 over 2. And this is what you were practicing on that worksheet and on the puzzle, is what is the arc whose sine is root 2 over 2? Now this time we're not just listing the one between 0 and pi, that was the domain of inverse cosine, we're listing all of them between 0 and 2 pi, and there will be 2 of them. And then we're going to attach a plus 2 pi k to each one of those to show that we understand that every time you go around 2 pi times 360 degrees, that you get another solution to this equation. Okay? So I like to draw a picture just to demonstrate where this happens. So there and there we have an arc whose cosine is root 2 over 2. And if you wanted to, you could call this one pi over 4 and this one negative pi over 4. That would be correct. Typically what we do, though, is we list all of them between 0 and 2 pi positive, and then just add a plus 2 pi k to it, where k is an integer. So the first one here would be pi over 4, right? So we have one solution is pi over 4 plus 2 pi times k. Or, down here, this would be, if I go all the way around this way, 7 pi over 4 plus 2 pi k. And somehow, we probably should state what k is, because k could be anything. It could be just whole numbers. It could be rational numbers, real numbers. We should probably state what k can be. So we need to state that k is an integer. And the way we do that is just write where k is an element of the integers. And sometimes you'll see kind of like they call it a chalkboard script or bold Z. They'll add another line in here to make it thicker or whatever. Just do that. But it's just k, this means is an element of z, and z is the symbol for the integers. You might want to write that down just for shorthand so you're not writing out where k is an integer every time. So just k is an element of that little backwards e, and then a capital Z is appropriate. You can just put a capital Z there and we'll know that you mean integers. So we use z for the integers. Capital R is the real numbers. Do you remember that? Q is actually the rational numbers. It's Q. Is that right? So when I say all solutions, this is what I mean. And I do like to draw a picture to show where that's occurring in one cycle, or one period, 2 pi. And then just add a plus 2 pi k to each of those. So for cosine and sine, 2 pi k. For tangent and cotangent, you're going to end up adding just a plus pi k because the period is pi for those. So those will have a little different expression, but similar idea. All right, number 2. We got a couple steps here before we even isolate sine theta. We got to first subtract the 1 over, right? And then divide by 2. So my next, I guess I could probably do that all in one step. Sine of theta equals negative 1/2. And then I'm where I was on number 1. And after this first one, we're not going to keep showing that we're going to take inverse sine of each side. We can do that, I think, in our heads and say that theta has to equal inverse sine of negative 1/2. So are we okay getting to that point? Theta equals inverse sine of negative 1/2. Move all that stuff over. So then I draw a picture. Where does this occur? What quadrants are we in? Are we at a reference angle of 60 degrees or 30 degrees? Picture this one. Sine. Yeah, it's 30. It's closer. So it's when, if I were to draw a picture, it would be right here and right here. So I'm trying to make it very clear, maybe exaggerating a little bit, that I am at a reference angle of 30 degrees or pi over 6. Okay. So I'm close to that x-axis as opposed to farther away down here. So theta equals inverse sine of negative 1/2 would be at what 2 places as I go around between 0 and 2 pi? Well, pi over 6, so it would be here. So I could add pi to that. So 7 pi over 6 is one of them, plus 2 pi k. Every time I go around 2 pi times. So when I say 2 pi k, if I plug in 1, I'm adding 2 pi to this. Okay? So it's just another 360 degrees. If I put in 0, I'm right at 7 pi over 6. If I put in negative 1, I'm subtracting 360 degrees from it, but still landing at the same point. See what I mean by k is an integer? So whatever I plug in, negative 1, 0, 1, 2, negative 2, it's just either adding or subtracting 360 degrees to that angle. Or the other one here, which one this is? Just before you get around to 2 pi, it's 11 pi over 6. 11 pi over 6 plus 2 pi k. And we should say where k is an element of the integers. And we'll just leave it at that. Okay, number 3. Says tangent of theta equals negative root 3. So we've got theta equals inverse tangent of negative root 3. Now, this one takes some thought. Draw my picture. Where is the arc whose tangent is negative root 3? If you're like me, you have to think in terms of sine and cosine. I don't know if you've memorized which ones are the root 3 and which ones are the root 3 over 3. Some of you may have. But how do I get a root 3 out of it? What is, so tangent is sine over cosine, right? So tangent is sine over cosine. I'll just write that down, just think about it. And then to end up with a root 3, I need to have root 3 over 2 on the top and 1/2 on the bottom. So what angle has the root 3 over 2? Which reference angle has root 3 over 2 on the top? That's the sine. In other words, it's farther up. And the 1/2 on the bottom is the cosine. Understand what that is? Pi over 3, the 60 degree at pi over 3. So that's what we're looking for here, is one that has the root 3 over 2 on the top and the 1/2 on the bottom. The 2's cancel, leaving just the root 3. Okay, so that is the 60 degree reference angle. So if I draw my picture here, well, now it also has to be negative, right? So what quadrants would I be in if it's negative when we're talking about tangent? Yeah, 2 and 4. Yeah, so right up here, up high though, 60 degree reference angle from the x-axis, and down here, but low, 60 degree angle, reference angle. Notice that both of these rays are just 180 degrees from each other, okay? And so when we write our expression, we can actually simplify it. We can do this with just one expression, believe it or not. So as I go around here, what is this angle? It's 2 pi over 3. And all I have to do is do plus pi k, where k is an element of the integers, and it covers, make this look like a z, not a 2, where k is an element of the integers. So that'll do it. If you wanted to show off and pick other angles and then put plus pi k on, you could. You could do negative pi over 3 plus pi k. That would be correct. It's fine to do that. But 2 pi over 3 plus pi k will cover all the angles. So any multiple, just have to, you take 2 pi over 3 and add pi, 2 pi, or negative 2 pi to it, and you'll land on an angle that works in this equation. So all we're doing is saying there's an infinite number of values of angles that you could plug in here and get negative root 3. Okay. And then if you're doing real life mathematical modeling, you want to limit it to a reasonable domain. Number 4. It's got a cosine squared in it. So first step will be to move the 4 over. So you have cosine squared of theta equals 3/4. And then when I take the square root of each side, it's kind of like if you have something like this, x squared equals 4. The algebra mistake is to only list the positive square root, right? But if we're solving that equation, we know that negative 2 also will make that true. So the same thing here. When I take the square root of each side, I get cosine theta equals plus or minus root 3 over 2. I'm taking the square root of the 3, the square root of the 4. And so theta equals inverse cosine of plus or minus root 3 over 2. And so in this case, when I draw my picture, I'm going to have 4 different solutions, 4 different rays coming out from the origin where I have an arc whose cosine is root 3 over 2. Now, the arc whose cosine is root 3 over 2, do you know which reference angle that is? 5 over 6, yeah. And so it looks like this. So trying to make those look close to the axis. So we've got right here pi over 6. So theta equals, I should really have, all these should be theta equals. So pi over 6. Now, I can take care of pi over 6 and 7 pi over 6 by just saying pi over 6 plus pi k, right? Or the next one is what's this guy right here? Pi over 6, yeah. Plus pi k. K is an element of the integers. Okay, so those are some basic equations. Listing all the solutions. All right. As we evaluate functions or solve equations, we'll sometimes end up with like one function inside of another. Composition of functions is pretty common. Something like this, we have a 2 theta in place of where just theta was, right? Or here we have a theta over 3 in place of where theta was. And so a common technique to use, a lot of students use, it's called U substitution. And that means just replacing this 2 theta with just a U and solving it like we did these up here, and then going back and plugging the 2 theta back in and solving for theta. So it's kind of a dual stage process here, 2 stages to it. Some students will use this, some are able to just kind of work with that 2 theta and not worry about the U substitution, and that's fine as well. But I want to show you this technique. It's something that we do use in calculus. As a matter of fact, when you get your list of rules for derivatives and rules for integrals, they're all in terms of U. And U, we have to understand, could be another function. There could be something else that U represents. And so it's worth understanding this technique. something as simple as this, I don't know if we necessarily need to substitute it for u, but we'll do it here. So here we're going to let u equal 2 theta. Okay, so if u equals 2 theta, then the new equation I have here is sine of u equals negative root 2 over 2. And I'm right back where I started with example number 1, straight up above that. Okay, it's just a single variable that I'm solving for. U, theta, doesn't matter. It's the same idea. So what I'm asking you to solve for here is u, first of all. U is inverse sine of negative root 2 over 2. And you can draw our picture. It's going to be down here and here, right? At the 45s. It's supposed to be at the 45s. So at the 45s. So in this case, u would be equal to what two values? 7 pi over 4 is 1. The other one is 5 pi over 4. So 5 pi over 4 plus 2 pi k, or 7 pi. I'm going to write it next to it here. Or, I'll show you why. So write it next to it, or 7 pi over 4 plus 2 pi k. Okay? So those are the two solutions. But that's what u is equal to. Okay, which we substituted out. What is u actually in this problem representing? 2 theta. So what this says is 2 theta actually equals 5 pi over 4 plus 2 pi k, or 7 pi over 4 plus 2 pi k. So what I'm going to do next is solve for theta. So what do I need to do to solve for theta? Divide by 2. Now if I divide by 2 on this side, I divide by 2 here, and here, and here, and here. And so theta equals, what are my new solutions? Now remember, 5 pi over 4, if I divide it by 2, it should get smaller. So keep that in mind. We were having a little trouble with that the other day. But 5 pi over 4 divided by 2, it's like multiplying by 1/2. So the 2 gets multiplied by the bottom of that fraction, right? So this is 5 pi over 8. And look what happens here. The 2's cancel, so I have plus pi k. It just means there are more solutions in a cycle as you go around. So, and then, or 7 pi over 8 plus pi k. And so those represent all the solutions. It's taking it step by step with the u substitution. But you could see, I could do this with 2 theta, just carrying 2 theta through the problem and then dividing by 2 at the end. I don't really need to do a substitution for something as simple as 2 times theta. It's not really a big deal. Just remember to divide by 2 at the end. Likewise here, I could probably just keep the theta over 3 and not do the u substitution, just multiply my answer by 3 in the end. Just don't forget to do that. But if I do a u substitution, this would be let u equal theta over 3. And so my new equation is negative 2 cosine u equals 1. And if I solve that for u, I have u equals inverse cosine of negative 1/2. I'm going to draw my picture here. So inverse cosine of negative 1/2 is going to be here and down here. Just a little ways out from the x-axis. So our cosine is negative 1/2 would be in the second and third quadrants. And so u equals, we've got 2 pi over 3 plus 2 pi k, or the other one is 2 pi over 3, 3 pi over 3, 4 pi over 3, plus 2 pi k. Then I go, okay, I need to replace u with theta over 3. Oops. Mess up on me. Okay, just give me a moment to do this real quickly. All right, so we have theta over 3. Having troubles. Theta over 3 equals all this mess, 2 pi over 3 plus 2 pi k, or 4 pi over 3 plus 2 pi k. And then I'm going to multiply through by 3. So we're going to multiply this by 3, this by 3, this by 3, and this by 3. That board is messing up. This is a pi right here. Unfortunately, you have it right above you. But the 3's cancel here, leaving me just theta equals, here the 3's would cancel, so it will just be 2 pi plus 6 pi k. Oh boy. Or here the 3's would cancel, leaving me just 4 pi plus, and then once again 6 pi k. We should probably say where k is an integer. Yes. So there it is. All right, one of the techniques we're going to use, it's the 6-letter F word in algebra. You know what that word is? It's the process we're going to use. Counting letters. Factoring. Yes, factor. F-A-C-T-O-R. Factor. You guys are factoring pros, right? So when I see something like number 7 here, by the way, the instructions are different. Now we're actually getting into what you might see with mathematical modeling. I'm going to limit you to between 0 and 2 pi. So in terms of time, that would be between 0 and about 6.28 seconds, right? 0 and 2 pi. So we're just keeping it on one cycle around the unit circle. So I'm only going to list the solutions. There's a finite number of solutions now. What I see here, let me just rewrite this for you, is 2x squared minus 3x plus 1 equals 0. That's what I see. Hopefully you see the same thing. I see a nice little polynomial-like function here. It's a quadratic equation that can be factored. Okay. You see it now? I actually put the smiley face there because I thought I'd draw smiley faces on each of these, but sometimes that confuses students even more. But it's 2 smiley face squared minus 3 smiley face plus 1. It's of the form of a trinomial, quadratic trinomial. Okay. So 2x squared minus 3x plus 1. You guys can factor that. It's no problem, right? It look like this. This. We know that it's 2x and x. And both signs have to be the same to get a 1 there. There's only one set of factors that multiply to equal 1. They are -1 and -1. But we're really not talking about x, or if you wanted to, you can use a u substitution here, or u. What we're really trying to solve for is sine of theta and then eventually theta, right? So I can replace the x with sine of theta. So this is really 2 sine theta minus 1 and sine theta minus 1 equals 0. So we have 2 factors, and what I want to do with those 2 factors is set each factor equal to 0, right? And that's the process we go through. We factor them first, and then we set each factor equal to 0. So I have 2 sine theta minus 1 equals 0, or sine theta minus 1 equals 0. Those are my 2 solutions. Now I'm back up like the problems that you saw in the first 4 examples, 1 through 4. Okay, we just have 2 little equations. What I think 2 sine of theta minus 1 we might already solved up there. I might have a different sign on it. But what this ends up being is theta equals, bring the 1 over, divide by 2. Oops, I forgot to carry over my inverse sine here. Let's try that again. So bring the 1 over, divide by 2, take inverse sine of each side. So I have inverse sine of 1/2. That's what theta equals for that first term. And then over here we have theta equals, bring the 1 over, take inverse sine of each side. So it's inverse sine of 1. So I have theta equals inverse sine of 1/2, or theta equals inverse sine of 1. So right here, theta equals, what is the arc whose sine is 1/2? Arc whose sine is 1/2. Draw a little picture here. That would be, oops, it's not going to cooperate with me. No. It's not going to cooperate. So it's low on the circle there. So we have theta equals pi over 6 and 5 pi over 6. And we're only listing those two. We're not attaching a plus 2 pi k to it. We don't need to. We're only listing all the solutions between 0 and 2 pi. And then here, theta would equal, it's straight up right here. So theta equals pi over 2 for that one. That's it. So 3 different solutions. In other words, if I plugged in pi over 2 for theta here, I would get 0. If I plugged in 5 pi over 6 or pi over 6 for theta, I would also get 0. Those are the 3 solutions between 0 and 2 pi that would make that equation equal 0. Okay? Zeros are pretty big deals. Finding zeros, you know, if we're finding zeros, that's the finding the places where it crosses through the x-axis. So finding zeros, important thing to be able to do. Right here, I've got the temptation here is, of course, to divide through by. You're thinking the same way I am. We look at this, we go, oh, I could get rid of that cosine of theta. Subtracting it is what you're supposed to do. Dividing is what we shouldn't do. Here's why. It's can't divide out cosine of x. It might equal 0, right? Cosine could possibly equal 0. If you think about the graph of cosine, does it go through the x-axis as it cycles through its parent graph? Yes, multiple times. So we can't divide by cosine because we could be dividing by 0. It would be like if I had 3x equals x. I don't want to divide each side by x here because x could potentially equal 0, and then I'm dividing by 0 and breaking the laws of algebra. Okay? So we don't want to do that. What we do want to do is subtract cosine of theta over and set the whole thing equal to 0 and then factor. Okay? Then we're not going to miss any solutions or break any rules of algebra. So now this is not a quadratic, right? So we're not factoring it into 2 different binomials like we did the previous one, but it can be factored. There's a common factor. You see it? Or if you remove this over, it would be x, right? So common factor is cosine of theta. Pull that out. So cosine of theta, and left over is tangent theta minus 1 equals 0. And so this is called the zero product property, is what we're using to split this into 2 separate equations. That's what that's called. The zero product property says that if I have 2 terms that multiplied equals 0, either this term equals 0, this term equals 0, or they both could. Right? So that's the zero product property. That's what we're basing this on. So we can set this up as either cosine of theta equals 0, or tangent theta minus 1 equals 0, and then I can solve each of those separately. Even though there's a mixture of 2 different trigonometric functions in here, I can solve this. So this is theta equals inverse cosine of 0. So theta equals the arc whose cosine is 0. Arc whose cosine is 0 happens at, remember? arc whose cosine is 0. When is the x-coordinate 0 if you go around the unit circle? Pi over 2, good. So theta equals pi over 2. And for this one, it's theta equals inverse tangent, or arc whose tangent is 1. So arc whose tangent is 1, it happens at 2 places. Pi over 4 is 1. Here we could draw a picture here. Pi over 4 is 1 right here, and then also pi over 4, and then, well, 7 pi over 4 would be a negative 1. So it's got to be 5 pi over 4 is the other one. So those are the 2 places where
Uh-oh.
yeah, that was that was the policeman warning you about dividing by 0. All right, number 9 here. We got number 9. Of what form is number 9? What type of trigonometric equation is this? It's a quadratic equation, yeah? You're starting to read math there. So yes, it's a quadratic. It's a quadratic equation in what variable? What's the variable? Yeah, that's weird. Yeah, it's a quadratic equation in the variable cotangent theta. Yes, that's how we describe this. It's a quadratic equation with the variable cotangent theta. So when I go to factor this, I'm thinking, okay, this is kind of like x squared plus 2x plus 1. Can we factor that? Yeah, we can factor that. This is easy factoring, right? X squared. Maybe we need to think about it as x squared plus 2x plus 1 still. That's fine. So how would that factor? Yep, x plus 1 times x plus 1. So, but it's not x, right? It's not x. It's cotangent x plus 1 and cotangent x plus 1. Or if you want to, you can think of it as cotangent x plus 1 squared. But either way, we have 2 of the same solution. Okay? 2 of the same solution. So I just need to take one of those and set it equal to 0. So cotangent of x plus 1 equals 0. So, no, it's not x though, it's theta. Let's change it to theta. So here we have theta as well. So have you thought about what theta equals yet? So if theta equals inverse cotangent of negative 1. So theta equals inverse, move that 1 over. Theta equals inverse cotangent of negative 1. So if I draw a picture here, that's going to happen here and over here. Theta equals inverse cotangent of negative 1. So what are those 2 angles? Over here we're at 3 pi over 4, right? The other one's 7 pi over 4, right? Remember, we're only listing the 2 angles between 0 and 2 pi, so we don't have to attach the plus or plus 2 pi k. That's better. It's kind of nice when it just says between 0 and 2 pi. You don't have to mess with that. All right, number 10. We're finally going to get to use that identity I showed you in the beginning. If you notice here, well, first of all, this is not in standard form of a quadratic. So let's go ahead and do that first. Maybe, well, do that first, or we could substitute first. Also notice that we have a mixture of variables. So we have a sine and a cosine. This is where the identity comes in, okay? So if I wanted to, I could move everything over here. I could have 0 equals 2 sine squared theta minus cosine theta minus 2. Pythagoras says, use me. Use the Pythagorean identity. So what do I replace sine squared of theta with? Well, it's going to take some thought. Go back to the identity, right? What does the identity say? I need to write this underneath Pythagoras here. It says cosine squared theta plus sine squared theta equals 1. That's what the identity says that we're memorizing. Okay, we memorize. So what does sine squared theta actually equal in terms of cosine squared? 1 minus cosine squared theta, right? Sine squared theta is equivalent to 1 minus cosine squared theta if I move the cosine squared theta over. Okay, so we're just rewriting this identity, the Pythagorean identity, and we're rewriting it so that it's sine squared of theta equals 1 minus cosine squared of theta. So I'm going to replace sine squared of theta with 1 minus cosine squared of theta. And what that accomplishes is now I have, by substitution, an equation in one variable. I need to clean it up a little bit here. It doesn't look like a quadratic trinomial to me, but we can make it look like one. So here I have 0 equals, this is 2 minus 2 cosine squared theta minus cosine theta minus 2. Oh, see if we're going to be better. 2 minus 2 cancels out. I really don't want the negatives there. I could move everything over to the, oh, this is a 0, not a theta. Everything over to the left. That's the problem with thetas. So I could then move everything back over to the left, or divide through by a -1, your choice. But this is 0 equals 2 cosine squared theta plus cosine theta if I divide through by -1. And then we're ready to factor this thing. So 0 equals, if I plot a cosine theta, I'm left with 2 cosine theta plus 1. And then I set each one of these equal to 0. Cosine theta equals 0, or 2 cosine theta plus 1 equals 0. So theta equals inverse cosine of 0, or theta equals inverse cosine of -1/2. And we've solved these already. So we'll finish this up. Theta equals arc whose cosine of 0, that was at pi over 2. Oh, I left out one earlier, huh? Here, arc whose cosine of 0 is also at 3 pi over 2. So add a 3 pi over 2 to that one. Arc whose cosine of 0 is pi over 2 and 3 pi over 2. And the arc whose cosine is -1/2. Draw a picture here. We're here and down here. So that's going to be theta equals 2 pi over 3 and 4 pi over 3. Alright. Don't leave before you get your homework. I have a worksheet here, but I want to just show you this one right here is another one where we have a substitution for secant squared. If you go back at the top of your page, you have an identity that involves secant squared. All the way up here, it's secant squared is the same as tangent squared theta plus 1. So if secant squared theta is the same as tangent squared of theta plus 1, I can simply replace it. And that's my first step, is replace with that identity. And then go ahead and move everything over. I've got tangent squared theta plus tangent theta, and then minus 2, if I subtract the 3 over, equals 0. And I've got a quadratic trinomial that is factorable. So tangent theta, one of them is plus 2 and the other one is minus 1 equals 0. And so tangent theta plus 2 equals 0, or tangent theta minus 1 equals 0. So if I subtract the 2 over, that's theta equals inverse tangent of negative 2, or theta equals inverse tangent of 1. And then you have to solve each one for theta. You have to solve each one for theta. Let me pass this out for you. So this worksheet covers sections 1 through 3. So it's a little bit of review as well. We thought about what the values are here.
Will the following students please report to the attendance office? Sam Fortius and Mary Loomis.
Yes. Yeah. Yep. Yeah, just let me finish this.
Yeah.
So theta would equal, here we've got pi over 4 and 5 pi over 4. If you look for an arc whose tangent is negative 2.
And I'm taking a picture of that.
Arc whose tangent is negative 2.
There's some more.
Go put it in the track of here.
I don't know, I'll have more later this week. Huh?
Mr. Randall,
Yes.